Okay, so I'm going to talk about exercise 11 to 10, which is to prove this theorem that isomorphism is an equivalence relation on groups. So here we talk about isomorphic groups. Isomorphic groups have a bijection that relates the two groups, and this bijection has this operation preserving property. So if I have two groups and I can find such a isomorphism between them, then they're called isomorphic. So there may be more than one such map, but as long as there's a mapping or a function between the two groups that satisfies these two properties, bijection and operation preserving, then these two groups are called isomorphic. Right? So the way that isomorphic is written is G, here I got twiddle equals H, or we just say G isomorphic to H. So what we need to do is show that this relationship between groups it defines an equivalence relation. Three properties are required, which you can see if you go back to the equivalence relations chapter. First, reflexive, that any group is isomorphic to itself. Symmetric, any group that's isomorphic to another group. Also, the isomorphism works the other way, that if G is isomorphic to H, then H is isomorphic to G. Transitive means that if you have one group isomorphic to a second and the second isomorphic to the third, then the first is isomorphic to the third. All right. So to prove all of these properties, what we need to do is exhibit isomorphisms that show that these groups are isomorphic. So these proofs involve showing isomorphisms. Oops, let me do this. Sorry. Okay. And we'll get there. Okay, here we go. Okay, sorry, let me get there. Okay. Okay, these proofs, or the proofs of 1, 2, and 3, of 1 through 3 involve, I can say this way, constructing and verifying isomorphisms. Okay, so for part 1, for instance, what we need to show that G is isomorphic to G is we need a map, we need a function from G to, let me just call it, well, we've been calling it phi, from G to G, such that phi is a bijection and phi of, let's write it this way, G1 dot G2 is equal to phi of G1 dot phi of G2. All right, so this is a function from the group to itself, and it preserves operation. So let me just give you a hint. There is a very simple function that you can define for any group, and it's phi of G. You can define it element by element. Phi of G is equal to something. Now remember, it's a function from the group to itself. What's the simplest possible function you can think of that would be a bijection? All right, you could do phi of G goes to the identity, but that's not a bijection. But there's a very simple function that maps the group to itself in a one-to-one onto fashion, and you can use that function to show the operation preserving property. Okay, so that's kind of what I want to say about in part 1. Part 2, what I can say is you need a function. So you're given, in part 2, you're given G is isomorphic to H. Means there exists, I'll write it this way, there exists a phi from G to H, which is an isomorphism. And you want to use this fact to find an isomorphism from H to G. And what I can say here is just you should use previous results in this chapter. Okay, if you look back a little bit, you'll find a place where, given these conditions, there's a way to construct an isomorphism from H to G. And for part 3 is similar. So for part 3, it's similar. You're saying given G is isomorphic to H and H is isomorphic to K, that means, this implies there exists a phi from G to H and a psi from H to K such that a phi and psi are isomorphisms. And you want to use this to construct an isomorphism from G to K. And again, you can use past results. We've seen something like this before. Okay, make sure that you shamelessly use past results. Don't waste your time reinventing the wheel. You want to build on results that you've done already. That's how mathematics makes progress. Okay.